Another kind of force that we're going to see on a regular basis is the tension force. Tension is the kind of force that is exerted by a string or a piece of rope or a chain or a cable or something like that. Basically anything that's bendy, so to speak. Now let's think about this. If I have this string attached to a mast like this, and we've got a stable situation, we know gravity is pulling down on the mass, but the string is pulling up. Now, you might say, well, my hand is pulling on it, but we're going to use the string as kind of an intermediary here, so to speak. My hand pulls on the string pulls on the mass. So, in what direction is the string pulling on the mass? Well, we know it has to balance the weight. If the weight is straight down, the string must be pulling straight up, right along the direction of the string. How is the string pulling on my hand? Well, if I am pulling up on the string is pulling down on my hand. Again, along the direction of the string. That is an important idea for tension. Tension always acts in the direction of the string, or the rope, or cable, or chain, or whatever. For example, right now the string is pulling the mass up. If I want to pull the mass to the side, can I just pull to the side like this? No, I actually have to take the string and point it sideways, and then I can pull the object this way. So we've got to keep in mind, anytime we've got the string in a particular direction, that's the direction of the applied force. So if we've got some object here and there is a string going off that way, the string is applying the tension, and the symbol that we'll typically use for tension is a capital T. We've got to be a little bit careful because capital T is also going to be used later on for the time that it takes for something to happen. It's typically something that's repetitive. The time it takes to happen once. We'll talk more about that later. But for now, we'll use T for tension. So whatever direction the string is in, that's going to be the direction. Of the tension being applied. Okay, this way, then the tension is for this one is this way, and we could have different tensions: T1, T2, T3. Also, for the time being, if this is attached, maybe this is your hand. Sorry, that's your hand. If this is attached over here, then likewise the string is also applying a tension on whatever's holding it at the other end. So think of the string as applying tensions everywhere through it, you might say, but in particular for us at both ends. So if we've got a string like this, the string is pulling this end up this way, but it's pulling this end down that way. So it's pulling in on both things, but in opposite directions. Okay? Great. Let's look at an example of applying tensions to an object. Okay, here we have a very typical type of tension problem. Let's imagine that we've got a mass here, let's say 20 kilograms, and there's a rope or a cable attached to it up here to some point, which then is attached to two cables, one cable coming over here being attached to a wall, and another one going up here attached to the ceiling. So let's imagine these are both stationary objects, a stationary wall and a stationary ceiling. And let's imagine that this rope goes up here at an angle of 20 degrees above the horizontal, while this one goes here at an angle of 10 degrees to the vertical. Let's see if we can figure out what the tensions are in these ropes, all three of them. Well, let's think about what's going on here. What we're going to do is actually focus on this point right here. You might think, well, isn't our object of interest in this case the 20 kilogram mass? Well, to start with, it will be to get one of the tensions, but what we're going to do is actually come up here and let's look at how all three tensions are acting at this point. Let's call this tension T1, and this tension we'll call this T2, and this one we'll call T3. Okay? if we think about how are these tensions all pulling on this point, T1 is going to be pulling down. T2 is going to be pulling up and to the right. T3 is going to be pulling up and to the left. Let's assume that this thing has been hung there and it's not moving, okay? It's a stationary problem. In other words, it's what we refer to as a static problem or a static problem. In other words, it's a non-moving problem. There's no motion involved. If it's not moving, what's the acceleration of this point? It's 0. If it's stationary, its acceleration is 0. Well, what's the net force acting at this point? If its acceleration is 0, the net force has to be 0. So if these three forces are the only forces acting at that point, the sum of these three vectors has to be 0. In other words, T1 vector plus T2 vector plus T3 vector must equal 0. Okay, well that's very interesting. If that's true, we can decompose these into an x and y part with scalars. Well, let's define an x and y axis and then we can do that. Let's define our x-axis, just typically horizontal and positive to the right, y vertical and positive up. So we can then, I didn't write this, but just remember x and y. So what we can do is decompose this equation and say t1x plus t2x plus t3x must equal 0, and t1y plus t2y plus t3y must equal 0. All right, there we go. So we've got these variables, the components of the forces in these two equations. Well, let's see if we can make any headway with this. First, let's come back to T1. Let's look at the 20 kilogram mass. We know that T1 is going to be pulling upward on T1. And if T1 is stationary, if the 20 kilogram mass is stationary, we know that T1 must just balance the other force that's acting on the 20 kilogram mass, which is its weight. And we know the weight is mg, or 20 kilograms times 9.80 meters per second squared, which is 196 newtons. Which tells us that T1 must be equal to 196 newtons. Okay, great. Well, what are the components? T1 is a vector that points directly in the y direction. So what is T1x? What is the x component of a vector that points along the y-axis? Well, it's 0. And what is T1y? What is the y component of a vector that points directly along the y-axis in the positive y direction? It's going to be 196 newtons. Okay, very, very good. Now, what about the components of T2 and T3? Well, let's look at T2, and what do we have? Well, T2 is at an angle of 20 degrees above the x-axis, so we can break this down like this, where this would be, if that's T2, this would be T2x, and that would be T2y. So what is T2x? T2x will be T2 cos 20 degrees, while T2y will be T2 sine 20 degrees. Now what about T3? T3 is up here at an angle of 10 degrees to the left of the positive y-axis. So we can decompose this, break this down like this, so that this length here would be T3y, and that length there would be T3x. So what are those components? Well, I'm going to write them down here. T3x will be T3 sine 10 degrees, but notice it's pulling to the left, so T3x has got to be negative. negative T3 sine 10 degrees. What is T3y? T3y will be T3 cos 10 degrees. Okay, very good. Just a little word of warning here. When you're decomposing these vectors, make sure that you're using the correct angle and you're using the correct sines and cosines. Remember, the adjacent side always gets the cosine, the opposite side always gets the sine, but that's not always going to be x, y, respectively. For example, here the x gets the cosine and the y gets the sine, but over here the x gets the sine and the y gets the cosine. So be very, very careful about that. Also, don't just assume that you'll be able to take our final result and apply it to any kind of problem like this, because what if this is T1 and that's T2 and that's T3? Well, then they'd have to get all moved around. So rather than just using our final result when we get it, it's much better to make sure that you solve the specific problem that you have with the definitions you're given and the angles you're given, and solve it that way. Okay, let's take these components and stick it in these equations and see what we get. Okay, before we put these components into our force equations, I noticed as I was doing that, I made a little mistake over here. With these components for T1, I was actually looking at the components of the force acting on the 20 kilogram mass. But when we look at the force acting at this point, notice T1y has to be negative, right? Because T1 is pulling downward on this point, so T1y is going to have a negative value, okay? Just let's make sure we notice that. Sorry about that, I should have said that before. All right, let's take our components. The x component will then be T1x, which is 0, plus T2x, which is T2 cos 20, plus T3x, which is negative T3 sine 10. All of those must equal 0. And then the y component will be T1y, which is negative 196 newtons, plus T2y. T2y is T2 sine 20, plus T3y, and T3y is T3 cos 10, and all of those must equal 0. All right, very, very good. Here we've got two equations with two unknowns. So mathematically, we know that we can solve this. How are we going to go about doing that? Well, I would suggest there are matrix methods of solving systems of equations. I just think it's much easier, especially when there's only two equations, to solve one for one of the unknowns and put it in the other equation. So for example, let's take the x equation. This minus that equals 0. Let's bring this to the other side, and let's divide both sides by cosine 20. And what do we end up with? We end up with T2 is equal to T3 times sine 10 degrees divided by cosine 20 degrees. Okay, there we go. Now, this is our solution for T2. Let's take this solution here and put it in here for T2. And then we'll have a single equation that only depends on T3, and then we can solve that for T3. Once we have our value for T3, we can come back here and solve this for T2. All right, I'm going to stick that in there, and then we'll solve it. Taking this term and putting it in here for T2, we have negative 196 newtons plus, now this is T2, T3 sine 10 over cos 20, then times sine 20, plus T3 cos 10, plus T3 cos 10 equals 0. Let's bring the 196 to the other side. We can factor off a T3 and divide by this horrible trigonometric thing, and what do we get? We get T3 equals 196 divided by this whole thing, sine 10 sine 20 divided by cos 20 plus cos 10. There we go. Multiply, divide all this out, and what do we end up with? We end up with 187 newtons. And that is T3. We come back here, put T3 of 187 newtons in here, and we get T2 equals 187 newtons. Sine 10 over cos 20, we multiply that out and we get 34.6 newtons. So there's T2. Here is T3. And T1 was 196 newtons. Just to check, let's go back to our original components. T1 is T1x is 0, T1y is negative 196, with T2 equal to 34.6 newtons. T2 cos 20 gives us 32.5 newtons. T2 sine 20 gives us 11.8 newtons. With T3 equal to 187 newtons, over here T3 gives us T3x gives us a negative 32.5 newtons, while T3y gives us 184 newtons. And then let's look at how these all add together. T1x, 0 plus 32.5 minus 32.5, well, that is certainly 0. And then the y component, negative 196 plus 11.8 plus 184. Well, 184 plus 11.8 is going to give us 195.8 that we have to round to the units place, which would be 196. So negative 196 plus 196, that also equals 0. All right, very, very good. So we've solved this kind of tension problem. One thing to keep in mind, I kept all the cosines and sines until the very end, but back here, you certainly could have just evaluated cosine 20 and have some number times T2 and some number times T3, and the same here, and then have some number times T3, and you could actually put it in and simplify it quite a bit before you get to this giant thing down here, and you just have 196 newtons divided by a single number, and it would work out pretty much the same way. Rounding things earlier always tends to give you a possibly give you a slightly different result than if you rounded at the very end. And basically leaving these in here, I rounded at the very, very end. So if you were to put the values in here, you might get a very, very slightly different result than I got. But that's absolutely okay. Okay, let's look at another example.